Today we are going to discover something truly beautiful, Fourier series, but not the way you have probably seen it before. We will see that Fourier series is just linear algebra in disguise. Let us begin. First, let us remind ourselves, what is a vector really? It is just a list of numbers. In 2 dimensions, we draw it as an arrow. In 3 dimensions, still an arrow. In 100 dimensions, still just a list of components. That is all a vector is. The dot product. You multiply matching components, then add them all up. It measures how much 2 vectors point in the same direction. If the dot product is 0, they are perpendicular. Simple, but this is the foundation of everything that follows. Projection. Take a vector v and a subspace w. Drop a perpendicular from v to w. The foot of that perpendicular is the projection. It is the closest point in w to v, the best approximation. Remember this geometry. It will become the Fourier series. An orthonormal basis is a set of perpendicular unit vectors. Each one points in an independent direction. Each has length 1. The standard basis, E1 and E2, are the simplest example. With an orthonormal basis, projection becomes very easy. When you have an orthonormal basis, the projection formula is beautifully simple. Multiply each basis vector by its inner product with v, then add them all up. That is it. Each term captures how much of v lies in that direction. Let us see an example in 3 dimensions. Take a vector v and an orthonormal basis w1 and w2 spanning a plane. Compute 2 inner products. Those give you the coefficients. Multiply and add. That is the projection. The math is clean and mechanical. Why is the projection the best approximation? Look at the geometry. The perpendicular from v to the subspace gives the shortest possible distance. Any other point in the subspace is further away. This is why least squares uses orthogonal projection. The least squares principle says the projection minimizes the distance. In symbols, the projection equals the unique g in w that minimizes the norm of f minus g. This formula works in any inner product space, not just vectors, functions too. Here is the formula that will change everything. G equals the sum over I of the inner product of f with wi times wi. One formula. Works for vectors in Rn, works for functions in C of AB. This innocent-looking sum is the Fourier series in disguise. Now the big leap. Can a function be a vector? A vector has n components. A function has a value at every x. That is infinitely many components. So yes, a function is a vector, just an infinite dimensional one. The key transition. A dot product sums products of components. As we sample a function at more and more points, that sum becomes finer and finer. In the limit, the sum becomes an integral. Integration is just the continuous version of the dot product. The function inner product, angle brackets f comma g, equals the integral of f of x times g of x dx. Same idea as the dot product. Multiply values at every point, then add them all up. The integral does the adding for us. Let us look at 2 functions, f and g. Their inner product is the area under the product curve. Positive and negative regions can cancel each other out. The net signed area is the inner product. This is how we measure alignment between functions. How long is a function? The norm. Square the function, integrate, take the square root. This is the root mean square value, or RMS. It measures the effective magnitude of the function, just like the Euclidean length measures the magnitude of a vector. When are 2 functions orthogonal? When their inner product is 0. The integral of f times g equals 0. This is the continuous analog of perpendicular vectors. Positive and negative areas cancel perfectly. That is orthogonality in function space. The classic example, sine x and cosine x. Their product oscillates symmetrically above and below the x-axis. The positive area equals the negative area. Total integral is 0. Sine and cosine are orthogonal on the interval from 0 to 2 pi. So C of AB, the space of continuous functions, is a fully legitimate inner product space. It has an inner product, a norm, a distance, orthogonality, projection, and best approximation. Everything you know about vectors applies to functions. All of it. To do projections, we need an orthonormal basis. For vectors, we have the standard basis, E1 through En. For functions, what should our basis be? We have to build one. And the tool for building orthonormal bases is Gram-Schmidt orthogonalization. Start with 3 simple polynomials, 1, x, and x squared. Apply Gram-Schmidt on the interval from -1 to 1 with the integral inner product. The result is the Legendre polynomials, a constant, a line, and a parabola, all mutually orthogonal. Let us see what they look like. P0 is a flat constant. P1 is a straight line through the origin. P2 is a parabola. Each one curves in just the right way to make its integral product with the others equals 0. This is the magic of Gram-Schmidt. The Legendre polynomials are orthogonal on the interval from -1 to 1. Change the interval or add a weight function, and Gram-Schmidt gives you a different family. Chebyshev, Legendre, Hermite, all from the same 4-step recipe. Now for periodic functions. The set of 1, sine x, cosine x, sine 2x, cosine 2x, and so on. These are pairwise orthogonal on the interval from 0 to 2 pi. No Gram-Schmidt needed. They come pre-orthogonalized. Nature gave us this gift. Let us verify. The integral of sine mx times sine nx is 0 whenever m and n are different. Sine times cosine is always 0. 1 times sine or cosine is always 0. Any 2 different trig functions are orthogonal, just like the standard basis vectors. But they are not orthonormal yet. The squared norm of 1 is 2 pi. The squared norm of sine nx is pi. Same for cosine nx. To make them orthonormal, we divide each function by its norm. Divide by root 2 pi, root pi, root pi, and so on. Now we have it. 1 over root 2 pi, sine x over root pi, cosine x over root pi, and continuing. An orthonormal basis for the space of periodic functions on 0 to 2 pi. This is the basis that Fourier discovered, and it changes everything. Why are sine and cosine so special? Because they are eigenfunctions of the second derivative. Differentiating sine twice gives -n squared times sine. Same for cosine. This means they naturally appear whenever you solve wave equations or heat equations. The common thread is Gram-Schmidt. Legendre polynomials are Gram-Schmidt on polynomials. Chebyshev polynomials are Gram-Schmidt with a different weight. Trigonometric functions are already orthogonal, so Gram-Schmidt just normalizes them. Same engine, different fuels. Now back to our projection formula. The same formula works in function space. The best approximation of a function f in a subspace W is the sum of the inner products of f with each basis function, times that basis function. It minimizes the L2 distance. What happens when we plug in the trigonometric orthonormal basis? We get the Fourier approximation. The projection formula applied to the space of periodic functions with the trig basis. That is all Fourier series is, a projection. Here is the Fourier approximation formula. G of x equals a0 over 2 plus the sum of aj cosine jx plus bj sine jx. The a and b coefficients are just inner products. Each term captures the contribution of one frequency. The Fourier coefficients. A sub j equals 1 over pi times the integral of f of x cosine jx dx. Bj is the same with sine. Each coefficient measures how much of f aligns with that particular trig function. These are the coordinates of f in the trig basis. Enough theory. Let us compute a real Fourier series. Take f of x equals x on the interval from 0 to 2 pi. A simple straight line. Nothing trigonometric about it. Let us see what the Fourier decomposition reveals about this humble function. Computing the coefficients. a0 over 2 equals pi. b1 equals -2. All the cosine coefficients, aj for j at least 1, are 0. Only the sine terms survive. This makes sense because x is an odd function about the midpoint. The first approximation, g1 of x equals pi minus 2 sine x, just one sine wave. The white line is f of x equals x. The blue curve is the approximation. It is rough, but it already captures the overall upward trend. Not bad for a single term. Adding more terms, g3 includes sine x, sine 2x, and sine 3x, each with decreasing coefficients. Watch how the blue curve hugs the white line more closely. More basis functions mean a better approximation. This is the power of orthogonal bases. With 5 terms, the approximation is very close to the original. The only noticeable gap is near the endpoints, where the periodic extension has a jump. This is the Gibbs phenomenon. Adding more terms will shrink the gap everywhere except at the jump. In the limit, as the number of terms goes to infinity, the Fourier series converges to f almost everywhere. For continuous periodic functions, the convergence is uniform. The trigonometric basis is complete. It can represent any reasonable periodic function. Parseval's equality says the energy of f equals the sum of the energies of its Fourier components. In symbols, the norm squared of f equals the sum of the squared coefficients. This is the Pythagorean theorem for function spaces. Energy is conserved. Why is this so profound? Because it reveals that every periodic function is just a combination of pure sine waves. Operations on functions become operations on coefficients. Differential equations become algebraic equations in frequency space. Fourier gave us a new coordinate system. Fourier's idea from 1807 powers modern technology. Audio compression, like MP3, decomposes sound into frequencies. JPEG image compression uses the discrete cosine transform. Quantum mechanics expresses wave functions as superpositions. Heat and diffusion equations are solved with Fourier series. Let us map everything side by side. Vector inner product corresponds to function inner product. Vector norm corresponds to function norm. Orthogonal projection corresponds to Fourier approximation. Coordinates in a basis correspond to Fourier coefficients. Same mathematics, different spaces. The universal recipe. Step 1, choose a basis. Step 2, apply Gram-Schmidt. Step 3, normalize to get an orthonormal basis. Step 4, project your function to get Fourier coefficients. This pipeline produces orthogonal polynomials, Fourier series, and much more. So here is the unified truth. Fourier series equals projection in function space. No magic, no mystery, just linear algebra in an infinite dimensional space. If you understand vector projection, you understand Fourier series. They are the same thing. Chapter 5 is complete. You now understand inner product spaces, Gram-Schmidt orthogonalization, least squares approximation, Legendre polynomials, the trigonometric orthogonal set, Fourier series, Fourier coefficients, and Parseval's equality, all parts of one unified framework. Linear algebra is the mathematics of everything.